Okay, beautiful day out. It looks like we've had maybe about an inch of snow. It's supposed to keep snowing pretty much till middle of the afternoon, I think. So the weather report's saying, depending on where you are, as much as 7 inches, but probably a maximum of 2. Anyway, it's kind of fun. I always hope for big snow because it makes life more exciting. We're going to continue talking about momentum and then work and energy. So we're now looking in chapter 3 of the textbook. I assigned the homework. I posted it yesterday. The homework has 3 questions from chapter 3. That's 3 questions from stuff that we're covering the end of last class period and today. And then the rest of the questions are from chapter 2, talking about forces. But let's digress a little bit. It's snowy outside. That means it's treacherous to drive your car, right? Why?
There's no grip.
Okay, there's no grip. In terms of physics, there's no grip means we have a low friction. So we often think of friction as a bad thing for our car, like the something that's going to, well, sometimes. We think of it as something that's going to cost us money because of friction and resistance. For a car, your primary loss of energy, something that's coming up in this chapter, is due to the air. The faster something's going through air, the bigger the force air puts on it. And so that makes the cars, the faster you drive the car, the bigger the air resistance, the bigger your energy loss due to that air. And that's where you lose almost all of your energy in the car. There's a little bit of energy loss in what's called rolling friction, because the tires are made to flex a little, and you're losing some energy in that. You'd actually lose less energy if you had tires that didn't flex. But then when you hit a pothole, it'd be a lot harder on the tire, and you would have to have more in your shock absorber system. But the friction is really important. The friction is what allows the car to move. In fact, the thing that makes the car move is friction. If there was no friction, you could press the accelerator and those tires could rotate all they wanted, but you wouldn't have anything pushing the car forward. So let's talk about what makes the car move and then move on into the lecture proper. So here's my car, and here's the drive wheel. There's another wheel because you do need wheels in front and back. And this drive wheel is spinning like that. The drive wheel is contacting the ground. And so if we just focus on that drive wheel, what forces are acting on the drive wheel? The wheel that power goes to in the car. Let's assume it's a motorcycle that way. You don't have 2 wheels. Go ahead. You were going to say something, Gabby?
No.
Oh.
Sorry.
Okay, we need to be able to identify forces. So I want students to actually answer and tell me what forces would be acting on that wheel, the black wheel with the arrow in it. Okay, we'd have friction. What direction is the frictional force going to be on the tire? It's the direction to keep it from sliding. And since the tire is trying to slide, it's trying to go this direction with respect to the ground's going to push the opposite direction to keep it from sliding. So we have that force friction. What other forces are we going to have? Okay, we'll have a force normal, which is going up to keep the tire from falling through the ground. Okay. Force gravity. Now, in reality, things are going to be a little more complicated for the car because the air flowing over the car will also put forces on it, right? And so what we usually write is there's also a force here that's force of air resistance. But you have other things. Let us suppose that this car has a spoiler on it. What is the actual purpose of that other than to look cool. Because sometimes the spoilers are simply there to look cool and are not doing their job that they're supposed to do at all. But what's the actual purpose of that spoiler? What?
Air.
Okay, he's doing something with the air. My son's totally into cars, so I'm becoming more and more aware of these kinds of things. The point of that spoiler is to get the airflow to push the car down more. Right? As that air hits the spoiler, the air is going to go like this, and it's going to push the car down. And so that's going to give you an additional downward force. Now, of all of those forces, which is the only one that can make the car go forward? There's only one pointing the right direction to make the car go forward, the friction. So it has to be the friction that's what makes the car move. Now, you stop and think about it, you're like, then what's the point of the engine? Well, the point of the engine is, if you look at Newton's third law, for every action there's an equal and opposite reaction. The engine is what's making the tire try to spin, and then friction is reacting to that, and that's what makes the car move forward. So if there's no friction, the tire can spin all at once, and you don't move forward. But with friction, then it goes forward. Now, I said this spoiler is to increase the downward force, so I'm going to draw one more arrow here. And they call it the down force, so I'll call it FD, the down force. The additional force you're getting from that spoiler that's downward. Why would that help you? What do you think?
It causes more friction, right?
That's right. It's going to create more friction. You can think of it real easily. I have my little piece of paper here. I slide it across here, and there's virtually no resistance to it sliding. But if I put something heavy on it, this isn't that heavy, but it'll suffice, then there's a lot more friction. Because it's heavier, it turns out that the force of friction is proportional to how hard you're pushing down on it. So if you double the down force, you're going to double the friction, which not only means that you could have a larger force pushing you before it slides, but you also are going to have better control before you slide sideways. So when you're going around a corner, which if you're looking at something like race cars, that's a huge thing for them. When you're going around a corner, if you have more down force, then you have more friction and you don't slide and you can go faster around the corner. So there's really good reasons for those spoilers when properly adjusted. Okay, now going to the actual topic du jour. We ended last class period with this slide and I think the next. So what was this slide? What was it illustrating? What's the point of those two pictures?
How fast can people slow down?
Okay, it has to do with how quickly something slows down. The time here is the time it takes to slow down. And so we had impulse, which is equal to the net force multiplied by the time over which it acts, is equal to the change in momentum. Which is mass times the change in speed. Remember that delta means change, and it means final minus initial. And hopefully it's starting to become more comfortable when I say change in and write delta. So we have the impulse is indicated with the Ft, and the change in momentum is indicated with the mv. And so you have in both cases the same mass times velocity. That is, the truck is going to have, the m is, remember I said that's representing the change in velocity. The truck starts with a big speed and ends with a speed of 0. So its initial speed is the change in velocity. Well, change in speed. What's the difference in velocity and speed? Direction. Velocity would have direction, speed doesn't. So it starts with a big momentum, and then when it hits the hay doesn't put a huge force on it, and so it takes a fair amount of time for it to stop when it hits the hay. So the big T is saying it's a small force over a big time to stop it when it hits the hay. Whereas if you look at it hitting the concrete wall, it's a big force over a small time. In both cases, you had the same change in momentum, went from its initial speed to a final speed of 0. So the impulse was the same, but one had a small force over large time, one had a large force over small time. And after this slide, we do have a clicker question, so just so you are aware. This here is a picture actually going with the very last thing I talked about in class. I talked about automobile safety and the devices we have in there to keep us safe. And we have things like our shoulder straps today have a spring system so that if you have to stop quickly, you come and you press on that and it gives a little. It gives a little so it takes more time to slow you down, hence decreasing the force by increasing the time that it's going to be active. The airbags are the ultimate in that. I don't know if this is a live action shot. I would not want to have the airbag deploy. Do you remember how fast these airbags are coming out at you? I think I mentioned it last class period. They come out at about 200 miles per hour. They have, I think it's sodium azide or something like that. They have an explosive in there. And when the car senses that you've had a large acceleration, it says, uh-oh, we've been in a crash. And it ignites that explosive to make the airbag come out at you like 200 miles an hour. If you're sitting too close to that airbag, it can hurt you. So I am pretty sure federal law requires that if you are really short, like 4'6", you can take your car to the dealership and you can have them disable the airbags because they're dangerous for you. If you get hit by the airbag, right? If you're really short, you're too close and it's going to hit you before it stops coming out. And then that can cause, lots of damage. So it comes out really fast, but then they just have big cutouts on the back, big holes, so that they don't hold air at all. And so they deflate very quickly, but they come out and they're not deflating so fast that they're not slowing you down. So they really extend the time for you to slow down, thus making a smaller force on you with this nice big cushiony airbag, making the damage to you not as significant, not as bad would be the right term. So the whole point of the airbag is to extend the time over which you change momentum, thus lowering the force you're feeling, because that force, you get hit with a hard force, it hurts. Not so hard force, not so bad. Okay, first clicker question. A fast-moving car hitting a haystack or hitting a cement wall. So that's situation 1 and situation 2. Produces vastly different results. Both experience, so what's going to be the same if your car hits a haystack at 60 miles an hour compared to your car hitting a cement wall at 60 miles an hour? Okay, everyone's answered. Let's hope it shows me. Nope, it didn't show me. I even put in a dummy question in hopes that it would show me. Well, poo on them. I will have somebody in this class. Danny, what answer did you choose, and more importantly, why? We don't have the feedback from everyone else, so you're kind of on your own to know if you answered what everybody else did. But of course, it's more important to answer right than whatever everyone else did.
I guess that it was A because I didn't fully understand the impulse thing, but it's changing momentum.
Okay. The impulse thing. Impulse is a term that means change in momentum. I don't like to use the term because we have another one that works just perfectly fine, change in momentum. So since impulse means the same as change in momentum, what would the correct answer be?
A and B.
Both A and B, which was D. Okay, because they're the same. So you are correct that they have the same change in momentum, but because change in momentum means impulse, they also have the same impulse. Somebody said, wait. Right, if we go back to the picture here, they both have the same MV, the same initial momentum, and the final momentum is 0. And then this one has a small f and a big T. This one has a big F and a small t. But in both cases, those had to equal. So what was different was how much force over how much time. The concrete is a very short amount of time and a large force. The haystack was a longer time with a lower force. Okay, conservation of momentum. Conservation in physics means doesn't change. So conservation of momentum is the situation when momentum does not change. I can give you a very, very simple example of where momentum does change and hence it's not conserved. If I take this ball and I let go, well, let's start. What's the momentum of the ball right now? 0, because momentum is mass times velocity, and the velocity is 0. I let it go, what happens to the momentum? It increases because then it has a velocity that's going down because of gravity. Gravity made it change momentum. So there's an example where momentum most clearly was not conserved. So it's not always conserved. You have to be in the right situation. And that situation we find just by looking at Newton's second law. Newton's second law, we said, was sum of the forces is mass times acceleration. Now, it's a vector equation, so let's put it like that. But we also know what acceleration is. What is the definition of acceleration? I went to the punchline. So there is a perfectly exactly the same replacement. Sum of the forces is mass times change in velocity over change in time. Now, if your mass is constant, the mass isn't changing, then that would be the change in mass times velocity over change in time is the same thing. Now, there is an if there. If the mass is not changing. If the mass is changing, then this step doesn't work. Here's the funny thing. What is MV? We have a simpler name for MV. Mass times velocity is momentum. This is really Newton's second law. That's really the second law. The net force is change in momentum over change in time. That net force is equal to mass times acceleration is only correct if the mass isn't changing. So what we've learned up to here for Newton's second law was the special case of if the mass isn't changing. But the true relationship is this one here. If I take this equation and solve it for for change in momentum, I just have to multiply both sides by change in time to get change in momentum by itself. And so there's a condition to relate the left side, change in momentum, the right side, impulse. And so we can look at that and we say, well, change in momentum is going to be 0 if either of the two things on the right side is 0. So what two situations, one of them is kind of ludicrous, the other one is the one we always focus on. What two situations would make change in momentum equal to 0? Just look at that equation. If this is 0, what does that say about this side? Okay, so if the change in time is 0, that one's the one that's kind of ludicrous. If the change in time is 0, that means if I take a picture at that moment, I'm not going to have momentum changing. It could change anytime before, anytime after, but not at that moment. That's just pretty obvious. What else would give us momentum being conserved, no change in momentum? If the net force is 0. So those are our situations where momentum is conserved. When we have a collision, let's say it's slick out there, I come to a stop sign too fast, and I can't stop. It's happened. Fortunately, I haven't hit somebody yet doing that. I can't stop. I'm coming too fast. If I hit somebody else, the actual collision, the time when I am hitting that person is a very short amount of time. And so in our problems, we'll say the time of the interaction, the time of the collision is very short. I have all of the time before the collision, have all the time after, but during the collision it's a very short time. So during the collision, momentum is conserved. Before the collision, I might have been on my brakes, and so my momentum would be changing because I have the force acting over that time. During the collision, even if I'm on my brakes, it's so short that we say the delta t is approximately 0, and momentum is conserved during the collision. After the collision, clearly we're both sliding, momentum is not conserved again. So for our purposes, anytime we have a collision between two things, as long as one of them is not, a big thing that's going to deform a lot, like the pile of hay, we'll say the time of the collision is so short the momentum is conserved during the collision. Not before, not after, but during. So momentum is conserved if the net external force is 0. Not internal force is 0. That's another thing. So if I take my ball, the external force of this ball is the force of gravity. That's not 0. Once I let go, net external force is not 0. So momentum isn't conserved. But this ball is interacting with the Earth. So if I make my system this ball and the Earth, then the net force acting on my system is going to be 0. And when I let go of the ball, the momentum of the Earth plus the ball has to remain constant. Of course, what happens to the ball's momentum? It goes from 0 to what? Its acceleration is 9.8 meters per second squared down. I was just looking for direction. It goes from 0 momentum to a downward momentum. If the momentum of the Earth plus the ball has to remain the same, what's going to happen to the momentum of the Earth when I drop the ball? Well, the sum of the two stays the same. The ball goes from 0 to down, so the Earth goes from 0 to up. So the Earth is going to have to fall up to the ball as the ball is falling down to the Earth. Once again, it seems bizarre and ridiculous. We don't notice the Earth falling up to the ball, right? They don't meet halfway. The reason for that is one of them has a lot more inertia than the other. the Earth has a huge amount of inertia, a huge mass, because remember, mass is measuring inertia. And so to get the same momentum, the momentum of this ball is its mass, really small, times its velocity. The momentum of the Earth is its mass, really huge, times its velocity. Because the Earth is somewhere around, let's say, 10 to the 24 times the mass of this ball. It's actually a little more than that. The velocity of the Earth is 1 divided by 10 to the 24th. That's 1 divided by 1 followed by 24 zeros. The velocity of the ball. So if the ball goes 10 meters per second, the Earth is going to be going somewhere in the ballpark of 10 to the minus 23 meters per second, which is 0 as far as you and I can tell. Hence, we don't notice it. One of my friends when I was in college, she thought her physics teacher was so great because he said, and when you see that beautiful flower and you pick the flower, the Earth moves. Because the flower had a change in momentum, and so the Earth had to have a rebound change in momentum. Of course, it's just the Earth moved by an imperceptible amount when you pick the flower. So examples. Now, when we do collisions, I said we're going to treat collisions as no change in momentum because the time is small. You do have to include both the colliding objects for that change in momentum to be 0. You can't say, well, I'm just going to look at one car and its change in momentum is 0. Not true. Both of them. So when I was in graduate school, I took my girlfriend to Riverfront Park in Spokane. We went ice skating. And I was like, oh, this is a great place for me to show her the kinds of things that I study. And so we're on ice skates. And so here's me, Richard. And here's her. Yes, she was much shorter than me, Nalco. And I said, okay, I'm going to show you a principle in physics. You stand very carefully. I'll stand very carefully. I'm going to push you. And then when I push you, we'll see who's moving faster. According to physics, we started both with a velocity of 0. So velocity of, well, let's keep color coordinated. Velocity of Nalco initially was 0. Okay, speed and velocity, it's one-dimensional. It really is okay to use either word here, but it is good to know the difference. Velocity of Richard initial is 0. What's our total momentum? 0. Because it's mass times velocity 1 plus mass times velocity 2. Now we push each other, or I push her. And so we have a push. If I push her, then she's going to have force of Richard on Nalco is going that way. But according to Newton's third law, if I push her, what's going to happen to me? I'm going to have an equal and opposite force. So there's going to be a force of Nalco on Richard that's exactly the same but in the opposite direction. And because we have these forces, we're both going to accelerate. Our times are going to be the same. So the force is the same, the time is the same. We're both going to have the same impulse but in opposite directions. And according to our rules, the net force on us is going to be 0. Why? We have a downward force of gravity, upward normal force, those add up to 0. We have negligible force of friction, so the only horizontal force are the force of Richard on Nalco and the force of Nalco on Richard, which are going to add up to 0. So we have the sum of the forces equals 0, therefore change in momentum has to be 0. And so we're going to have, in the final case, velocity of Richard final like this, and velocity of Nalco final like this. And we can calculate the momentum total
momentum final is equal to the mass of Richard times the velocity of Richard final plus the mass of Nalco times the velocity of Nalco final.
If momentum's conserved, what does that final momentum have to be? 0, because it started at 0, and if momentum is conserved, momentum initial is equal to momentum final.
So conservation of momentum says momentum initial equals momentum final. 0 is equal to, well, let's just put it right here. So this is equal to 0. And so then we can calculate right away how our speeds are going to relate. Let's just go ahead and calculate Nalco's speed. So I have to get the velocity of Nalco by itself, the first thing I do is subtract away the other term. Come on. And I have and then to get the velocity by itself, I have to divide the stuff it's multiplied by that's not velocity. And so I find for my end result, the velocity of Nalco final is equal to minus the velocity of Richard final times the mass of Richard over the mass of Nalco. Now, my mass was twice hers to a very good approximation. So that would be equal to minus 2 velocity of Richard final.
What does the minus sign mean here? Is what? Yeah, what does that mean? Opposite direction. So I'm going one direction, she's going the opposite direction. And because my mass is twice her mass, it's going to end up she's going twice as fast as I am. So I was a genius. I did this. I'm demonstrating physics. Think she was excited about learning physics? What do you think she was? She fell down and was angry. I told her I was going to push her. She didn't say, no, don't push me. And she was angry. Terrible, terrible thing to do on a date, it turns out. But I have to add, okay, so this is all a true story. The worst part of the whole story is when I took off my skates, one of my feet was just soaked in blood. The sock was totally red. I was like, oh man, I must have had a blister. It didn't even hurt. I took off my sock. I didn't have a blister. They had given me a skate that was filled with blood from somebody else.
That's so gross.
Yeah, it was kind of gross. That was a great date. So, elastic collisions. We have two kinds of collisions. We're going to have a lab this week on collisions. So you're going to have the carts, and you're going to make them bounce off of each other or stick together. Those are the two fundamental types of collisions we're going to look at. An elastic collision is when the two things bounce off each other and they don't lose any energy. We haven't talked about energy yet. So all we can say right now is they just bounce off each other perfectly. That's an elastic collision. An inelastic collision is one where they don't bounce off each other perfectly. Now, there's a lot of variations on inelastic collisions, and we will simply restrict ourselves to the other option is they stick together. So in our experiments, you can tell there's magnets in this, right? We have carts that have Velcro on them and magnets. And so with the carts, you will adjust the carts so that you either have them stick together with the Velcro, making an inelastic collision,
or should you have the magnets repel each other, making an elastic collision? And yes, this belonged to this cabinet, so I'll put it backwards along. So we have those two types of collisions. They're still going to have momentum conserved during the time of the collision. The momentum should be conserved anytime we have a fast collision. Or if the external force is zero. We're going to put these on our tracks that have very low friction, so to good approximation, momentum is conserved during the collision, no matter which kind of collision it is. But you have distinctly different outcomes. If you're playing football and you have a safety come barreling in and he wants to hit the receiver, if he just puts his shoulder into him, the two will bounce off each other, right? And so the safety's coming in, let's say the receiver, let's say it's what the New Orleans Saints safety, whatever Williams, hoped would happen at the end of the football game last week. He hoped he would come in, he would put his shoulder into Stephon Diggs' back and drive him backward. He would go flying, fall down, stay in bounds, and the game would have been over. Would have saved Viking fans a huge amount of pain this week. So let's suppose that was what happened. What kind of collision would it be if he hits Diggs while Diggs is up there in the air and Diggs bounces off of him? Would it be elastic or inelastic? It would be elastic because they bounced off each other. Now keep in mind, it's not perfectly elastic, but we are going with that approximation. So it'd be elastic collision. Diggs was basically not moving forward or backward when he jumped up for the catch. And so he would have gone from stationary to all of a sudden flying back toward the quarterback after the hit. And Williams, coming and hitting him, what would he have done? Okay? If he was up in the air, there are a couple things that could have happened. It depends on his mass. If Williams had more mass than Diggs, then he would have kept going just at a slower speed. If he had less mass than Diggs, he would have actually bounced backward. But the fact is, Williams should have had speed on the ground so he could drive and continue supplying force. And if you continue to supply force, then the whole momentum conservation thing is going to be thrown off. He's going to keep going because he's supplying force, right? So we talked about specialized situations, but there's an example where we can see what should happen. And so that's like the first picture there, A, where Stephon Diggs would be the yellow one, stationary going up for the catch. Williams would be the green one, comes in, hits him, and if they're the same mass, then Williams would have just stopped and Diggs would have gone on. Now, if you have two people coming head on toward each other at full steam, that's the middle one, where they both bounce backward. And then the last one, what if they're going the same direction? They hit each other, the one behind slows down, the one in front speeds up. The goal is for him to speed up enough that he falls down, right? That's not good football, though. Everybody understand it's not good football to just hit somebody? You guys care about football? No. No, Leslie's really adamant. No. Well, what you're supposed to do is wrap them up. Instead of having an elastic collision where they bounce off of you and could potentially land on their feet, you hold them to you. You make them come down to the ground with you. Then they can't keep going. That's what you're supposed to do in football. If Williams would have wrapped him up. Of course, there's some other questions like, was he getting there too early? Was he trying to avoid pass interference? It's not big, especially since you don't care about football. But that would be an inelastic collision where they stick together, and it's the way you're supposed to do it in football, just so you know. So here's an example of an inelastic collision. You have two things coming together. They stick together, and you have the final momentum. In both of these situations, got to be careful. In both these situations, momentum initial is momentum final. Momentum is conserved during the collision. In the elastic collision, the math is a little more complicated.
So we're going to keep it to simple things. We're going to keep it to like, we'll give you the velocity of all but one of them, like the velocity of both of them initially and the velocity of one at the end, and you calculate the other one. So you're just going to be doing mass 1 speed of 1 initial plus mass 2 speed of 2 initial equals mass 1 speed 1 final plus mass 2 speed 2 final. And if you have all of the numbers but one of them in that entire equation, you can solve for it. Sticking together is more fundamental. You have mass 1 V1 initial plus mass 2 V2 initial is equal to mass 1 plus mass 2 V final. Why is that one simpler? Because they end up with the same final speed. And so in this problem, you can see they tell us in the problem, actually they should have told us, it doesn't say the words. When I was going over this, I noticed. Mass 1 is supposed to be equal to mass 2 here. Question?
Yeah, I was just gonna ask, how is it in the equation that the velocities are the same? Is it because it's out of the parentheses, it's gonna be the same, or?
You're talking what I just wrote?
Yeah, like, understand.
Because they stick together.
Oh, their final velocities are gonna be the same.
Yes.
Oh,
Because they stick together. So that's what makes it simpler here. And so in this problem, they didn't say, but it's supposed to be two identical cars. So mass 1 equals mass 2. And if V1 is 10 meters per second and V2 is 0 meters per second, then we can just take this equation and say V final is equal to mass 1 V1 initial plus mass 2 V2 initial over mass 1 plus mass 2 and here I used M for mass 1 and mass 2 because they're the same. Well, that's not very hard. That's M times 10 meters per second divided by 2M. I can cancel these M's. And I have V final is equal to 10 meters per second divided by 2 equals 5 meters per second. And so you can see that's what was done here in the problem. They calculated the final speed because they stuck together. It didn't take a real lot of work. Now, if I had had the same situation here, right, this is the same fundamental situation, I'm going to have to either know what this speed is or this speed to finish it out. I need one more piece of information. If you have a higher physics class, you don't need that one more piece of information, but like I said, it's more complicated, so we're not going there. So here you would have to have, V1 initial, let's say that's 10 meters per second, and V2 initial is 0. That's given in my picture. And then V1 final is 0. There I've given you 3 of the 4. Now you can solve it by moving, well, since those are 0, they just disappear. And V2 final is equal to M1 over M2, V1 initial. And if M1 is equal to M2, that's equal to V1 initial. So those are how we do these conservation momentum problems. What you're going to be doing in lab on Thursday is checking to see if these things are true. Right? Lab is where you check to see if what I'm telling you is what really occurs. So you're going to do different collisions, and you're going to measure the momentum before and after the collision, as well as the kinetic energy before and after the collision, and see if they're conserved. Do you guys have questions, or is it? Okay, fire away.
We're just trying to figure out the formula.
Okay. The one that's on the screen now?
Yeah.
Okay, I started with momentum initial is equal to momentum final. That is, momentum is conserved because it's a collision that occurs in a short period of time with no external forces. We have both the conditions for momentum conserved. Then I replaced momentum as mv. So momentum initial is mass 1 times velocity 1 initial plus mass 2 times velocity 2 initial. So I took mv for each of the objects before the collision. Equals, and then on the right-hand side, it's mass 1 times the velocity of 1 final plus mass 2 times the velocity of 2 final. So that's the final momentum on the right-hand side. Then from the pictures, I took that this was V2 initial equals 0 and V1 final equals 0. So I took those values from the picture. So that's the 0. So I have arrows saying, okay, this whole term is 0 because the velocity was 0. And so that left me with an equation that I actually did not write, an intermediate equation. Now, this is only true for this collision, for collision A. Because collision A is where I had V2 initial and V1 final were zeros. And so then from the purple equation, I just divide both sides by M2 to get V2 final. So is that clear now? And do ask me when you have questions, because if you just leave saying, I don't know what he did, he wrote some stuff, it really doesn't help you very much. Leslie.
So you're not given any of the masses at all? How would you figure out?
Okay.
M1?
In this problem, again, it was supposed to be implied that M1 equals M2 equals M, which is why I have this right here, the M1 equals M2, so those cancel. You have to be given the masses as well.
Okay, yeah.
And
Yeah.
the pictures show them the same size, and you're supposed to say, they're the same mass. But that is not given, and it may not have been correct. Could have been one's made of lead and one's made of, plastic. And that would make a huge difference.
But typically you're given the mass.
Yes, typically you're going to be given the mass. Like the example I did with me and Nalco. I didn't actually give you the masses, but I did say that my mass is twice her mass. Where did I say that? I don't know. I didn't actually write it down. I only said it. Or to be more exact, my mass at that point was just a little bit less than 100 kilograms, and her mass at that point was around 50 kilograms. I'm sure she's heavier now. Hope so. Okay. We have just enough time to define work, and then we'll have to quit for the day. So work. We all know what work is. I'm working right now, right? Anything you do to make a paycheck is work. In physics, we have what we call work is technically mechanical work. And mechanical work is a force that makes something move parallel to the force. So it's not just applying a force. Just applying a force is not work. You have to apply a force and it has to move. So if I have this remote in my hand, right now I'm applying a force. What direction is that force? Up. I'm applying an upward force. If I didn't, it'd fall. So I'm applying an upward force, but I'm doing no mechanical work because it's not moving. Now, if I walk like this at a constant speed, my force is still up, and it's moving, but it's moving perpendicular to the force. Work has to have motion parallel to the force. So if I'm pushing up but moving horizontally, it's still no work, no mechanical work. So how do I do mechanical work? Well, if I apply an upward force and it moves up, I did work on it. If I apply an upward force and it comes down, I did a negative work. Or it did work on me. So important things, work is force times distance parallel to the force. And if the distance moved is
the opposite direction of the force, then it's a negative work. If the distance moved is perpendicular to the force, it's no work. Leslie.
Is it negative because of the fact that you have like, I'm just curious to know this, because is it because the force of gravity is also pushing down on it, and if you're just there, it's kind of like your work is zero, but if you're pushing against it, I guess, would that changes it, or?
We will learn very quickly, work is a transfer of energy. And so if I'm pushing it moves the same direction I'm pushing, then I'm transferring energy into it. If I'm pushing it's moving the opposite direction, then I'm taking energy away from it instead of putting it in. And so that's why it's negative.
All right. I guess we'll stop there. So we'll continue on with work and energy on Wednesday.